Thank you, Mr. Chairman. Now, let me introduce our studies on the hydrogenation of Crotonaldehyde or Crotonaldehyde. Crotonaldehyde is an unsaturated aldehyde and has CC double bond as well as CO double bond. By hydrogenation of CO double bond, chlorhydrate alcohol is formed, and this reaction has long been a target of catalytic reaction. But hydrogenation of CC double bond is much easier than that of CO double bond, and so butyraldehyde is formed over typical hydrogenation catalysts such as nickel and palladium. And butyraldehyde is further hydrogenated to butanol. And this route was used for industrial production of normal butanol. In order to produce chlorhydrate alcohol, we must prepare catalysts which has high selectivity toward CO hydrogenation, not to CC hydrogenation, and not to hydrogenate chlorhydrate alcohol to butanol. We drive this selective hydrogenation reaction over cobalt-based bimetallic catalyst. The reaction was carried out in a stainless steel autoclave, and 1 gram of catalyst with reactant decomposition was packed in the catalyst reactor. Ethanol was used as a solvent, and the initial hydrogen pressure was 10 atoms, and the reaction temperature and reaction time are shown here. First, we tried this reaction over various metal catalysts, group 8 metal catalysts supported on aluminum. Normal metal catalysts such as ruthenium, rhodium, and palladium produced only butyraldehyde, and formation of chlorhydrate alcohol was not found at all. Similar result was obtained also over nickel catalyst. In contrast to these highly active catalysts, the catalysts with moderate activity, cobalt and platinum produced a small amount of chlorhydrate alcohol. In order to improve the selectivity of this cobalt catalyst, we tried to prepare bimetallic catalyst. In a preparation of bimetallic catalyst, we have proposed a new method to use volatile complexes as a starting material of the second metallic component. This figure shows an example of the preparation steps of kappa-promoted platinum aluminum catalyst. Left side shows the conventional method to use inorganic salts such as copper nitrate. When it is supported by impregnation, it distributes on the catalyst surface uniformly. And because the precursor is fixed on the catalyst surface, it is reduced at the same position as supported. And finally, copper distributes not only on the platinum surface but also on the surface of support. And interaction between two metals is not sufficient. Instead, when right side shows the case when we use volatile complexes as the second metallic component. The precursor distributes uniformly on the support when it is supported by impregnation. But when it is heated up for reduction in a flow of hydrogen, it starts to migrate on the catalyst surface because it has volatility. And when it came in contact with the platinum particle, it is decomposed because the ligand is hydrogenated by the action of catalytic activity of platinum surface. And finally, most of copper deposits selectively on the surface of platinum particles. Such a method of preparation was applied for the preparation of cobalt-based bimetallic catalyst. As a precursor of second metallic component, we used three types of complexes. One is acetyl-acetonate complex. Another is dipivaloid metallate complex, which is similar to acetyl-acetonate. Last one is the ferrocene type cyclopentadienyl complex. The cobalt-based bimetallic catalysts were prepared as follows. First, we prepared cobalt alumina catalyst, and then we changed it to bimetallic catalyst. The prepared starting material, cobalt alumina, was prepared by impregnation of cobalt nitrate solution. And then it was calcined in air and reduced in hydrogen flow, and then the complexes of second metallic component was added as a benzene solution. And the solvent was dried up in vacuum and reduced. The complex was reduced in hydrogen at this condition. And after reduction, the catalyst was transferred into autoclave without exposing to air. This figure shows the result of the series of cobalt-based bimetallic catalysts. The starting material, cobalt alumina itself, has about 40% of selectivity toward trotyl alcohol, but the formation of byproducts were larger than the main product. By the addition of second metallic components, some catalysts decrease the activity and some catalysts increase the activity. Among these, zirconium, titanium, and ruthenium suggested a good promotion effect, especially by addition of zirconium compound. The formation of byproducts were only 1/3 of the original cobalt alumina catalyst, and the yield of trotyl alcohol was 3 times that of cobalt alumina catalyst. Similarly, by addition of titanium and ruthenium, the yield of trotyl alcohol increased very remarkably. This figure shows 3 types of promotion effects. By the addition of chromium, the formation of byproducts, butylaldehyde, decreased very markedly, but the yield of trotyl alcohol also decreased a little. So chromium promotes only the selectivity, not the activity. In contrast, by the addition of ruthenium, both trotyl alcohol and byproducts increased, and selectivity was not so promoted. So ruthenium promotes only the activity, not the selectivity. By the addition of zirconium, both selectivity and activity was promoted remarkably. And the best catalyst was found here. This original cobalt alumina catalyst, and the yield of trotyl alcohol was 3 times that of cobalt alumina catalyst. Similarly, by addition of titanium and ruthenium, the yield of trotyl alcohol increased very remarkably. This figure shows 3 types of promotion effects. By the addition of chromium, the formation of byproducts, butylaldehyde, decreased very markedly, but the yield of trotyl alcohol also decreased a little. So chromium promotes only the selectivity, not the activity. In contrast, by the addition of ruthenium, both trotyl alcohol and byproducts increased, and selectivity was not so promoted. So ruthenium promotes only the activity, not the selectivity. By the addition of zirconium, both selectivity and activity was promoted remarkably. And the best catalyst was found here. This